Okay, so here's my announcement board. First off, you have chapter 3 homework, and I bumped the due date back. So it was scheduled to be due Wednesday night, the night before the exam, and I would still prefer you to do it the night before the exam. It's just that we aren't finishing that material till today, and I wanted to give you a couple extra minutes. Like, if you don't want to fully submit the assignment, but you want to work on it some, I just wanted you to be able to like fully study for the exam. Although I think doing the homework will help you study for the exam. Okay, so anyways, it's just not due on mastering till Friday at midnight, but the syllabus is not updated yet. So just be aware that this is due Friday. Okay, you also have quiz 3 today. So that should be live now. And don't do it during lecture, obviously, or you might miss something important here, but you have till the end of the day to do that. Just our typical format, 5 multiple choice questions, 20 minutes to get it done. It's timed assignment. So don't forget quiz 3. Let's talk about exam 1. So here's some really important stuff about exam 1. Number 1, do not forget to sign the academic integrity form. Okay, that's this right here. On the quizzes, I have you sign those. I've had it in the past, and it just happens. And I know they never intend to, but I've had some students not sign that. And I think they just forgot. I think they just got busy looking at the questions and were like, oh, I'll come back to that. Just don't forget. Just do it first thing, okay? It puts me in a really tough spot if you don't sign that, okay? Because I've said on there, you can't receive above a 0 if you don't sign it, okay? Because you're committing to do the exam with integrity. And so if you don't sign it and it's just because you forgot, well, how do I know it's just because you forgot? I'm going to assume that because I genuinely believe nobody would intentionally not sign it. But it just puts me in a really tough spot. So please don't forget to sign that. Also, there may be a question, probably just one, where you have to upload an image of your work. Okay, has anybody had to do this in the past for other classes? You can shake your head. Okay, so if you have not had to do this, I'm going to recommend something to you. I think whether you have an Android or an iPhone, there is an app called Scannable. Okay, it's blue and it has like a little butterfly or something on it. It's an app that I recommend. Students last semester loved it. It allows you to hover over a document with your phone. So I will allow you to use your phone to take a picture of your work, and it converts it directly into like a PDF. Okay. Now you can upload a JPEG or a PDF to the exam, but other formats sometimes don't work out well. So I really prefer you upload any pictures of your work. There may be times you have to handwrite out your work, take a picture of it, upload it to exam, JPEG or PDF, and that will be in the instructions. This just sometimes causes students stress because it's something you do, but then it's you got to keep in mind, save a couple minutes either during the exam or afterwards to take a picture and transfer the document and upload it. So I understand that takes a couple minutes. You're going to have 2 hours to take the exam, which is much longer than our class time. We only have an hour 15. So if we were in person, you'd only have an hour 15. So you have plenty of time. If you have any questions about or doubts in your mind that your document did not upload correctly, just email me a picture of your work, okay? And as long as you don't, as long as you've emailed me right then and there and not like hours later, okay, where that could be questionable, did you work on this problem later? If you've emailed me right then and there, I'll see the timestamp, then I can accept work via email, okay? But please try to just upload it to the exam. I just highly, highly recommend this Scannable app. I don't think it costs anything. If you have questions on that, let me know. So you will have to upload an image, one picture of your work to the exam, and I don't want that to stress anybody out. I prefer JPEG or PDF format. You guys, 8 a.m. section, you'll be getting on Thursday at 8 a.m. You have to take the exam at our lecture time. So if you hop on at 9:30 or in the afternoon, the exam, you'll have missed it, just like a normal class. Okay, so treat this as an in-person thing. You are taking it at 8 a.m. You have to log on. It will be live from 8 a.m. to 10 a.m. for you, and that's it. So please don't miss that. It will be password protected because I do have a group after you guys and I want them to take it at their time. So I will email you the password by 7:30 a.m. that morning. Okay, I will email you that password. So check your email at 7:30 a.m. You'll have the password. When you log on at 8 a.m. to take the exam, you'll put in that password. Any questions so far on the exam? It's worth 100 points. And I will, when I go back in and grade, I will add your bonus points as I'm grading. So those won't be initially added, but as I grade your exam and then go evaluate your response to the bonus point question, I will add those in, which, by the way, the opportunity to receive bonus points is now gone. You had to respond to the discussion board question by last night, and I can see what time people put their responses in. Because we're going to talk about the answers to those today, because I want you to feel confident with those style of questions. All right, so that's the exam. Now we're going to talk about the dry lab. The conversions dry lab. There was some issues apparently with reporting numbers in scientific notation, specifically for this problem right here, okay? We may have to report numbers in scientific notation in future. So that's why I want everybody to know what I meant when I put all those instructions and things. I see something in the chat, hold on this problem, the assignment. Okay. Question in the chat, if you want to meet on Zoom at any point with people or to study, I'm pretty sure you guys can meet for up to an hour. I think it should be free because you have UCA credentials. Beyond that, you may have to just start another Zoom or take a break and meet up later. I don't know. I don't think you can do meetings, and it may only be 45 minutes. I'll try to check on that, but I know students last semester would form study groups via Zoom and meet for like 45 minutes and then maybe take a break and meet again, okay? So there you go. Bailey says, hey, everybody, we're starting a study chem group. If you wanna join, check the group chat. Perfect, thank you, Bailey. All right, let's look at this really quick. So this problem, I'm just gonna do this one right here. You had 1,055 milliliters, and I ask you, no, today's not about review, Gabby. We will finish chapter 3 in just a second. I just need to address this because you may have to type an answer in this way on the exam or future assignments, the way I had you do it for the dry lab. So let's convert it to centiliters, milliliters to centiliters. So first off, we need a relationship. I know that 1,000 milliliters equals 1 liter, and I know that 100 centiliters equals 1 liter. Okay, so because these both equal 1 liter, they equal each other. So 1,000 ml equals 100 centiliters. You can simplify this if you want, or you can use this relationship. It does not matter. If you simplify it, it's just that 10 ml equals 1 cl, okay? So now let's do the problem. We have, I'm gonna move up here, 1055. I'm gonna turn this sideways. ml, we wanna cancel out ml, okay? I'm just gonna use this one right here, this relationship. So there's 1,000 milliliters for every 100 centiliters. And then you cancel out milliliters and you divide by 1,000 and multiply by 100, or in essence, you're dividing by 10. So it should be 105.5 CL. On the dry lab, I said, okay, you need to report this number in scientific notation. You needed to report all your answers for this problem in scientific notation. So we need to make this number 105.5 a number between 1 and 10, right? Because that's the rules for scientific notation. So to do that, we're going to move the decimal 2 places to the left. Now we have 1.055. And then remember, our decimal moved 2 places left, so the exponent increases by 2. So that should be times 10 to the power of 2. So this is the number in scientific notation. And then I gave instructions that people use the shorthand letter E, okay? And E is gonna stand for this portion right here, okay? E. And then you're just gonna type your exponent. So the way I wanted you to enter this in Blackboard was 1, and I told you 3 decimals. I've told you how many decimal places for each. If I tell you 3 decimal places, I talked to someone yesterday who thought you only put the decimal places in. No, you still have to put the number that's left of the decimal place. You still have to put your base number. But I'm just telling you, to the right of the decimal, how many digits to go. And I said, I want all 3. So it should be 1.055 E2 because it's a positive 2 on the exponent. If it was a negative 2 exponent, you would type negative 2. So this is how I wanted you to enter answers into Blackboard. Okay. I'm kind of deciding what to do. I'm trying to assess this problem and see how many people just bombed it and how many people did it correctly. And I'm going to make a decision on that as to whether this problem is just for credit or extra credit on the dry lab. Okay, so your grade might get adjusted. I'm not making any promises on that yet. I haven't decided what I'm going to do. I need to just assess further how many people did not do this correctly, okay? I know that was a lot of instructions, and here's what I also know. You guys can work your tail off on an assignment and spend a lot of effort and a lot of time, and then you feel nervous because if you just type it in one little thing wrong, Blackboard counts you wrong. I get that, and I hate it just as much as you do. Okay, this is not how I'd prefer to do chemistry. Okay, so don't think that I want it to be this way. I hate it for you guys, and I really do try to imagine and account for all the different possibilities and way people will accept or type in answers, and spend the time on the front end when I design the assignment so that you guys don't have to worry about, do I put a space or no space? Do I capitalize or not? Okay, so I try to account for those things. If you ever have questions on a lab assignment about your grade, just email me. I'm happy to look into it for you. I just don't know to look at it unless you email me, all right? Questions on that? Okay, we've got to move on because we got a lot of other, I'm gonna go back to my notes. So that is this one, check. Okay, I posted the key, by the way. If you go into the labs folder now, if you wanna see how I worked all the problems on the dry lab out, ignore the fact that there's point values next to each problem. That's for TAs. They've graded these things in the past, but you can see how I worked everything out. So look at that and you can use that to prepare for the exam. All right, discussion board questions. There was some great discussion. How many responses did we get? We had 77 responses, 77 people getting bonus points. That's wonderful. Okay, so let's look at these. The first question on the discussion board. So I'm not going to be able to, actually, I'll just share my screen. You're not going to be able to see anybody's responses. I just want you to see what I'm looking at and we can talk through them. Good Lord. All right. Share screen to my desktop now. There we go. Okay, can y'all see? I don't know what y'all can see. Can y'all see the discussion board questions? Okay. So number one, right here. Formation of a precipitate involves a change from things that are liquid to forming something solid. So why is this considered a chemical change and not a physical change? All right. How is formation of a precipitate different from the process of freezing, in which a change from liquid to solid occurs? Would a substance that freezes be considered a physical or chemical change? Okay, so a lot of questions there. First off, formation of a precipitate. Why is it considered a chemical change? Can anybody answer this? Why formation of precipitate is considered a chemical change and not physical, even though we're just having things that are liquid mixed together and we form a solid?
The chemical makeup changes.
Yes, thank you. Okay. New product, the precipitate, is a different compound. Okay, it is a different compound. So the chemical composition has changed. That's why it's a chemical change. All right. How is formation of a precipitate different from the process of freezing? Who wants to share that? A lot of people responded. So who wants to say what they said on that?
The process of freezing is just the change in matter. The chemical makeup of it doesn't change.
Right. So the arrangement of the molecules. Solids, things are held close together. Liquids, things are spread more apart. Gases, things are spread even further apart. But the chemical identity, the compound or the element, does not change. Okay. Now, I saw some people said, there was one response that what was it? I have it right here. I wanted to address this. Freezing involves a temperature change, so it's a chemical change. Somebody said that. They said freezing involves a temperature change. Okay, you're getting colder, or you could apply that to melting. Melting involves a temperature change, so it's a chemical change. That's not true. Think words like melting, freezing, boiling, evaporation. These are physical changes, okay? Yes, maybe you apply heat to melt something, but you've not changed the chemical identity, okay? A temperature change means that you are roasting or cooking or combusting or burning something, okay? Words like burning, roasting, combusting, exploding, those are all chemical changes. But melting or things that do sound like they involve heat, okay? You have to assess, is the chemical composition of my original compounds changing or staying the same, all right? Okay, so something that freezes is a physical change. All right, number two, right here, consider the process of dissolving a packet of sugar into some hot coffee or tea. Is it a physical or chemical change? Most everybody got this correct, but dissolving something is just a physical change. The sugar molecules are large crystals. We can see sugar molecules, but when you put them into your hot coffee or tea, they dissolve and they spread out, but the sugar itself has not changed. That's why your tea or your coffee tastes sweet, because the sugar molecule stays intact. We don't change that molecule. We don't change the chemical composition of the sugar or the coffee, even though it has a different taste. We've just mixed two things together. So that's a physical change. And so dissolving is not a chemical change. Lastly, number 3, currently when my daughter asks for juice, I fill a cup halfway with the apple juice and then dilute it with some water. Don't judge me, she doesn't need all that sugar. What does a physical or chemical change occur when I dilute the juice? If so, which one? This is a physical change. Adding water, diluting something is a physical change. Okay, we're not changing the chemical composition. So I wanted to go over those answers for you guys. Basically, the point of this discussion board was to let you know diluting and dissolving things are physical changes, not chemical. All right, so hopefully you feel good with that. And now we're going to go back to the iPad and we're going to get into lecture. Any questions so far on everything we've talked about? I know that was a lot. So if you were glazed over just then, I will post the recording of this later and you can catch up on anything you missed, but we need to go into lecture and I need to scroll up. Okay, this is where we ended off last week. And now we are just going to finish chapter 3 and then we'll do some review at the end. So we talked about ions. We wrote these out, how to write out the symbols for ions. I call this a symbol because it's just the elemental symbol and the charge. We also looked at how to write out the names a little bit with Roman numerals, with transition metals, but that's what we're really going to talk about today. Okay. When do you write the name? When do you write the symbol? How do you write the formula for a compound, which involves more than one element? I'm going to skip over this practice problem because we're going to do something similar to this in our review today. So the title of this slide is writing the names of cations. So first off, writing the full name of a cation and writing the symbol for a cation is different. The symbol is what you did is like this. You just write the elemental symbol and the charge. The name, as you can see, is the full name of the element. Okay, so they're different. If I tell you to write the symbol for the ion, or if I tell you to write the name, know what I mean. Okay, so how do you do this? Well, first off, for cations, we have 2 different kinds of cations. We have main group cations. So what groups are main group cations found in? Can anybody tell me? What groups are main group cations found in on the periodic table? Main group cations.
1, 2, 13 through 15.
So main groups are just, it'll be 1, 2, and 3. Elements in main groups 1, 2, and 3. If we scroll up right here, this is main group 1 with hydrogen. This is main group 2, and then you skip the transition metals. They're not main group metals, right? So you skip over to, that's a 2. Skip it over to 3 with boron and aluminum. That's main group 3. All right, so we're going to name these differently than transition metals, which is everything down here. These are all the transition metals. So we're talking about main groups. And all you do is you name the element and you put the word ion. It's that simple. You name the element. So for example, K+ will be the potassium ion, magnesium ion, aluminum ion. We do not use Roman numerals. No Roman. I'm just going to put the number sign. No Roman numerals for main group elements because their charges are predictable. They only form an ion with one kind of charge. Unlike transition metals, and we saw Thursday, sometimes transition metals can form different charges. Questions on that? All right, now let's talk about the other kind of cation, which is your transition metal cations. And these, because sometimes they can form different ions with different charges, excuse the old name here. This is just kind of a Latin form of stuff, and we're not going to use that in this class. So I'm just going to focus on the new naming system. There may be times you see the old naming system on the internet if you're reading about things or different places, but we're going to use the new naming system. So you name, if you're going to name it, you put the element name. So Cr2+, this is the one we're talking about right here. This is chromium. So we would write out the element name chromium. It's a 2+, and sometimes chromium can be a 3+, right? You see over here. So we've got to differentiate. Are we talking about the +2 version or the +3 version? So we're going to put the Roman numerals for 2. And if anybody's unfamiliar with Roman numerals, you just do a 1/ for a 1, 2 slashes for a 2, 3 slashes for a 3, and then a 1 and a V indicates a +4, okay? So if we're talking about the chromium 3 ion over here on the right, again, you name the element chromium, Roman numerals for 3, and then you put the word ion. This is if we're naming an ion or if we're writing, whether it's transition or main group, okay? Questions on how to name cations. That's it. That's all the rules for cations. All right. Anions. Okay, what is an anion? Is an anion something that gives or receives electrons?
Receives.
Yes, thank you, Bailey. Receives. So these things are negatively charged. The way we name them, these are all found mostly on the right side of the periodic table. Okay, so main group 6 and 7, sometimes main groups 5, 6, and 7. So you see halogens, all right? Bromine, chlorine, fluorine, iodine. These are all your halogens. Oxygen and sulfur are main group 6. These are all main group 7. So there's the symbol for all these ions, but the name is what I want to teach you. How do you name these? You write the name of the element, but you change the ending. Okay, notice the last 3 letters I'm going to underline in all these cases are IDE, IDE, IDE. So when you're naming an anion, you change the end of the element name to "ide." Okay, IDE. So bromine, the element bromine as an ion becomes the bromide. You put the word ion, bromide ion. Chlorine as an ion, an anion, becomes the chloride ion. Oxygen, we take off the last half of that word. It's now the oxide ion. And then sulfide, same thing. Okay, so that's how you name anions. That's the only rule. Change the name ending to "ide" and you put the word ion. Questions on that? All right, so this is how you name ions. Now we're going to talk about how you name compounds. After, I forgot, we got to talk about polyatomic ions. Somebody asked me about these, and maybe I think they put a picture in the group me or are going to. You have polyatomic ions that you need to memorize for the exam, and it's these 11. Okay, because I very well could ask you to name a compound that has a polyatomic ion in it. And if you don't recognize the polyatomic ion, you're not going to name it correctly, and you'll miss points for that. Okay, so when I say know it, I want you to know both the name. So for example, this first one, know the hydronium ion. If I say hydronium bromide or something like that, you would need to know this formula, H3O, and that it has a +1 charge. You need to know the formula and the charge on that formula, and you also need to know what name corresponds with that. Okay, so there's 11 of these. I'm telling you, things will be a lot easier for you on exam 1 if you just memorize these, because you will need to recognize them for naming compounds, naming ionic compounds. Okay, questions on these? All right, it's straight rote memorization. Okay, now let's talk about compounds. How is a compound different than an element? Can anybody tell me? Remember, we got to classify matter. Elements and compounds are different.
There's more than one like element.
Yes, okay. More than one element. Now, going back up here, if I'm looking at these polyatomics, there's more than one element. Why aren't these compounds? We're still calling these ions. Why is this not called a compound if there's more than one element?
Because they have a charge. They didn't like cancel out.
They're charged, okay? So compounds, that brings up an important point. Compounds are neutral. Overall, they have no charge. If there's a charge, it's an ion. But if it's neutral, it's a compound. So all ionic compounds have to be neutral. Okay, now ionic compounds generally form between a metal, and your metal will be your cation, whether it's a main group metal or transition, and a non-metal. Remember how we divided up the periodic table into yellow, blue, and purple colors? We looked at that on the atoms periodic table lecture. And I showed you which elements all were metals, which ones were metalloids, and which ones were nonmetals. So you pick a metal and you pick a nonmetal and you can get an ionic compound. These are your anions, the nonmetals. So for example, here's two examples here. The first one, we've got potassium ions. K plus is K is potassium, and F minus, this is fluorine. So when you put these together, you make the compound potassium fluoride. You got your metal, which is your cation, and your nonmetal, which is your fluoride ion. Number two, calcium oxide. Okay, we've got the calcium metal, and we've got the oxygen nonmetal. And together, they make the ionic compound calcium oxide. Okay. Notice, and we're going to go over these rules, but the metal, the cation, always comes first. In these two examples, and in every time you write an ionic compound, the metal, the cation, always comes first, all right? And then the nonmetal comes second. All right, let's look at what's happening. Remember, this is all due to transfer of a valence electron. Okay, the cation has given away a valence electron. The anion has received that valence electron. Sometimes it's just the transfer of one valence electron, but oftentimes it's the transfer of 2 or 3 valence electrons. So let's look at potassium and fluorine. Potassium is main group 1, so it's got 1 valence. Fluorine, you see the 7 valence electrons here on fluorine. So this 1 valence is going to go to fluorine, and when you get done, now we have the K plus ion. Remember, you could write it, you could understand underneath the first shell, now it has a full set of 8, but it's more commonly accepted to write group 1 and 2 elements that become cations with no valence electrons, and you just write their charge on them, okay, when they become ions. So K does not have 8 dots around it. It has no dots around it. And then fluorine has a full set of 8 in its outer shell because it received that 1 from potassium. Now it's got a minus charge. All right. Calcium, guess what? Main group 2. There's the 2 valence. It's ready to give both of those. And oh, it just so happens that oxygen wants to get 2. Oxygen has 6 valence and it wants to gain 2 more. So this is a perfect agreement. Calcium's happy to give 2 away, and when it does so, it becomes the +2 cation. And then oxygen receives those 2, and it's now got a full set of 8 in the valence shell, and now it's a -2 anion. Okay, so all of this stuff is stuff we talked about last week, and now I'm just showing you the full reaction picture. So if I were to ask you to write out a reaction, show the electron dot structures or the electron dot symbols of your elements and then your ions as products, this is what I would mean, okay? You write out a reaction like this. Okay, so how would we write the names for ionic compounds? What if we switch some things around? What if potassium is going to bind up with oxygen? Okay, we got a metal and a nonmetal. We can form a compound out of this. But here's what I know. Potassium only wants to give away 1 valence electron. Oxygen wants to receive 2. So what do we do? How can we make a compound out of this? Potassium only wants to give 1 valence. Oxygen's not satisfied until it gets 2. You need 2 potassiums. That's correct. You need 2 potassium ions. Okay, so we're going to put a 2 here. And now we can, each one can give away 1. And so we'll form 2 potassium ions. Now oxygen will have a full set of, I guess I should do these other ones in black to show the ones it originally had. Had 6 originally, it gets 2 more. And now overall, it's a -2. All right. And you see how if we write the compound for this, we would just write K2O. And everything adds up to 0. We've got 2 plus charges and 1 -2 charge, and everything adds up to 0. So that means the compound's neutral overall, right? Oh, I think I was just going to write that down here. K2O. How do we name that? Great question, Bailey. After we examine this slide, we're gonna talk through all the rules for naming. I'm gonna teach you how to name compounds. You're gonna name the ions, but you drop the word ion. So this one would just be potassium oxide, right? See how we've still denoted this as an anion by naming IDE, but you don't say potassium ion oxide ion because now we have a compound. Okay, so it's just potassium oxide. You drop the word ion. We'll walk through some rules with that. Okay, what about with calcium and chlorine? Now it's the same problem, but it's from the anion side. The anion here, well, chlorine's not an anion yet, but chlorine only wants to receive 1 valence. And calcium's like, no, you got to take both. I've got to get rid of 2. So how do we solve this dilemma? If we have 2 chlorine atoms, now each chlorine can accept 1 so what am I trying to say? Electron, 1 electron from calcium, and both of the calcium valence electrons can be given away, and you get Ca2+. You can write 2+ or +2. Doesn't matter if the 2 or the plus comes first. And we get chlorine is now going to have, we'll have 2 of these. I didn't leave myself enough room. So we'll have 2 chlorine, and here's all the valence now that chlorine's going to have. And one of these was given to it from the calcium. So now this is going to be a minus. But we have 2 of them because each chlorine atom accepted 1, so we get 2 chlorine anions. So calcium and chlorine, how would you write the formula for the compound overall? How would you write that? We've got 1 calcium cation and we've got 2 chlorine anions. Just like we did for the potassium oxide right here, how would we write the formula for calcium chloride? Yep, I'm seeing it in the chat. CaCl, and we gotta remember we've got 2 chlorine anions here, so we're gonna put a 2 down there. That looks like a G. We've got to fix that. CaCl2. So in that situation, the only thing that changes is the 2 in front of it, right? Not the charge. Correct. We're only changing the number of anions we form, not the charge. We can never change the charge. Remember, these things are predictable and they're set. The only time you can have different charges on stuff are transition metals, okay? They can have different charges. Chlorine will always be a -1. So don't ever tell me chlorine will be a -2. It's just that you have 2 chlorine or chloride anions. Each one is a -1. Great question, Rachel. So how would we name this? It would be calcium chloride, chloride, calcium chloride. Not calcium ion, chloride ion. It's just calcium chloride. All right, any questions on this stuff? I'm going to teach you something. You're going to run into some questions on the Chapter 3 homework that this is going to be helpful for. Some of you have already done it, and you've kind of figured it out, and I think that's great. But in case you've not done that yet, I'm going to teach you something called the switch trick. Sometimes people look at charges, and it's hard to figure out, okay, how many cations and how many anions do I need in my formula for my compound overall? And the switch trick is going to help you for that. So we are going to make this compound right down here. It's called magnesium phosphate. Phosphate, you probably don't recognize it because you're new with polyatomics, but phosphate is a polyatomic ion. All right, PO4. It's all one unit. So we're going to look at the charges on the anion and the cation before we put them together in the compound. Okay, so the charge on this ion, what is this ion? This ion is the anion. The charge on your anion on phosphate is a -3. All right, and the charge on this ion, which is the cation for magnesium, is a +2. Okay, we got a +3 and a +2, or -3 and a +2. How many cations, how many anions do we need to get a neutral compound overall? So what that means is the amount of positive charge and the amount of negative charge, they have to add up to 0. So we do the switch trick. What that means is the charge on this anion, the anion, is the same as the number of the other ion, okay, which is the cation in this case. So that means we need 3 cations, okay? So the charge on your anion matches the number of cations you need in the formula. We call this the switch trick. You're switching the number. The number for the charge on the anion becomes the number of the subscript of cations you need in your formula. You see that? And then the charge on the cation is the same as the number of the anion. We need 2 phosphates. So let's double check ourselves. Does this add up to 0? Well, we have 3 magnesiums, and each one is a +2, right? We got 3 of them. I'm looking at this subscript here. Each magnesium from the blue up here is a +2, so I'm going to do 3 times +2. I got 3 of them. Each one's a +2, so that makes +6 overall. That's how much positive charge we have. Okay, what about phosphate? Phosphate, we've got 2 of them. All right, I'm looking at this subscript here, the blue 2, and I've got, each one is a -3, so I'm going to do 2 times -3, and that adds up to -6. And +6 and -6 all add up to 0, which is neutral. So this is a neutral compound. So this is the switch trick. The only other thing you have to do is you have to make sure everything is simplified, right? So you cannot simplify 3 and 2. That's as simple as it gets. But if you had like Mg6PO44, this would still be balanced, charge neutral, but these subscripts right here can be simplified. How can they be simplified? They can both be divided by 2, all right? And that's where you get the 3 and the 2, okay? So ionic compounds must be written as a formula unit. And that's what we just kind of derived. It's the simplest ratio between the cation and the anion with the smallest possible, it's neutral overall, okay? Smallest possible neutral unit. So just make sure you simplify in the end. Okay, questions on what we just did. We're going to practice a lot of this stuff. Okay, because this stuff is the newest, I encourage you to spend a lot of time this afternoon and tomorrow on this stuff. Hopefully over the weekend, you spend a lot of time on chapters 1 and 2, and now you can mostly spend the remaining time preparing for the exam by spending time on chapter 3. All right, here's the rules for writing compounds. We've addressed a few of these things as we've gone, but here's just, if you want a page to come back to, again, you can use your notes and your lecture slides on the exam. Write the cation first and the anion second. Okay, remember the example there earlier with like calcium and oxygen? You should write CaO, not OCa, okay? Not that one. The metal, which is your cation, comes first. The non-metal, which is the anion, comes second. Okay, rule number 2. Do not include the charges on the ions. And again, this is for when you write compounds. If you're writing ions, you got to include charges. But when you put them together and form compounds, you delete the charges. So we write CaO, not Ca2 plus O2 minus. We can deduce the charges from what we already know about ions and their organization on the periodic table. So we don't have to write those when we write the compound overall. Okay, rule number 3, use parentheses around the polyatomic ion formula if it has a subscript, meaning you need or have more than one polyatomic in your formula. I'm going to read this again. You've got to use parentheses around your polyatomic ion formula if it needs a subscript, meaning you need more than one. So for example, when we did the magnesium phosphate, we had 3 of these. PO4 is phosphate, that's a polyatomic ion, and I needed 2 of them. If we don't include the parentheses, look what happens. Mg3PO42. Now it looks like you have 42 oxygens in your formula, which is not going to happen. And that's not correct. We need 2 phosphates, not 42 oxygens, right? So it's not this. Same thing if we had aluminum hydroxide. Aluminum is a +3 cation, so we're going to need 3 hydroxides. You don't have to know all this right now. I'm just writing an example for you. It would be OH, and OH, each OH is a -1, so we need 3 of them to balance that aluminum cation. And so if you only write Al OH3, this is incorrect because it looks like you have 3 hydrogens, and you need 3 hydroxides, not 3 hydrogens. You need 3 of the entire unit. So the parentheses indicate everything within the parentheses is multiplied by 3. Okay. Questions on this? I got to turn my space heater off. Okay, questions on this? All right. Let's keep going. So now I want you to practice. I want you to take these ions. I've given you the name of the ions, not the symbols, by the way. So this is even more challenging because you need to first, I encourage you to write out the symbol with the charges for the ions. Then put them together and write the compound, and we're going to name that compound. So give me the formula and the name of the compound. So we got sodium ion and chloride. If you have a periodic table, grab that. That's going to help you. I'm going to work the first one, maybe first two with you. Sodium is Na. That's main group 1. So what charge should we have on sodium?
Positive.
Positive 1. Thank you. Chloride is main group 7. Chlorine's main group 7. So it only wants one valence. So it's a Cl with a -1 charge as an ion. So we're going to put these two things together. How many sodium cations, how many chloride anions do we need for it to get a neutral compound, for everything to add up to 0? How many cations, how many anions?
Just 9.
Thank you, Maria. 1 each. So we just need NaCl. So that's the correct formula. Now let's name it. We just dropped the word ion here. We don't have any transition metals. We don't have to worry about Roman numerals. So it's just sodium chloride. We don't have any polyatomics here. So it's just sodium chloride. Okay. I'll give you a hint. If some of these, again, this is why you have to know your polyatomics. Sulfate is a polyatomic. Bicarbonate is a polyatomic. Phosphate is a polyatomic ion. So if you want to know how to write these, you need to go look at your polyatomic ion chart. These are 3 of the 11 that I ask you to memorize. So iron 3 ion, what is that? Iron is Fe. And we see from the Roman numerals, it tells us what the charge is. So this is going to be a +3. Sulfate, can anybody tell me? Sulfate is SO4. Can anybody tell me the charge on sulfate? It must be the anion. So it has to have a negative charge because it's second. Remember
Negative.
Thank you, Brooklyn. We always write cations first, anions second. So I want you to try the switch trick if you need to. Remember the rule. I'm going to scroll up for just a second. Number 3, we've got a polyatomic here. So if we need more than one, we've got to use parentheses. So there's a lot of rules coming into play with this one. We've got a transition metal. We've got Roman numerals. We've got a polyatomic. There's a lot of different rules at play here. Anybody tell me what you got? I'm going to write my cation first. Fe. How many cations do I need? How many irons?
2.
Yep, you can always do the switch trick. So remember, the charge on here, it becomes the number of irons that we need. So we're going to do 2, and then I see Ashton said and Grant said Fe2, and then it should be SO4, and you got to put parentheses around that because we need 3 of them. Okay. And when you double check, does everything add up to 0? It does. Okay, how do you name this? Well, here we cannot lose our Roman numerals. It's going to be iron 3 sulfate. You just drop the word ion. That's it. You keep the Roman numerals because it's a transition metal. Why did we not have Roman numerals for sodium? It's a main group cation, not transition metal. Okay, now we have sodium ion plus the bicarbonate ion. Again, we wrote sodium earlier, so it's just Na+. Bicarbonate, this is a polyatomic, so you need to look at your polyatomic chart. It's also known as the hydrogen carbonate ion, but I call it bicarbonate. So if you see bicarbonate, I would encourage you to be more familiar with that name. That's more the medical term for it too. This is HCO3-, -1. So putting these together, how many cations and how many anions do you need for overall your compound to add up to 0? I'm looking at the charges when I consider this. I got a +1 and a -1. So if I just have 1 each, it should add up to 0. Na, H. So if I just need 1 of this polyatomic, do I need parentheses? Do I need to write this?
No.
Put a 1? No, I don't. Just writing the polyatomic is good enough itself. So you don't need the parentheses there. Okay. So how do we name this? We just drop the word ion. We have no Roman numerals here because we don't have any transition metals. So it's sodium bicarbonate. All right, last one. We have ammonium. Whoa, this one's also a polyatomic. I didn't see that earlier. Ammonium is also a polyatomic, and phosphate. We have 2 polyatomic ions here. So we might need a lot of parentheses. I don't know. We'll see. What is ammonium?
NH4.
Yep, NH4. And it's got a plus charge. Thank you, Sarah. Phosphate. We looked at phosphate a couple slides ago when we learned the switch trait. So if you remember that one, it's PO4, and it's got a -3 overall. So we got to write a compound that's neutral. We got a +1 and we got a -3. So what can we do to manipulate these numbers to make it add up to 0? We got to have 3 of these, okay? 3 times +1 adds up to +3, and then a +3 and a -3 add up to 0. So that means I need 3 of these. Remember, you can always do the switch trick. Thank you, Ashlyn. I see she wrote the formula for us, NH4. I'm going to need 3 of them. So guess what? I got to use parentheses here. That 3 indicates I have 3 of my ammonium ions. And then you got PO4. We only need 1, so we do not have to use parentheses on the phosphate because we just need 1. And then that we've already made sure that added up to 0. So then how do we name this? We just drop the word ion. It's ammonium phosphate. Okay. Pretty good practice. You're going to have to do this on the exam for sure. Questions? There's a lot more practice problems here, and I don't have a poll. I did not have time to throw that in, so that's from an old lecture. But I did want you to remember how to name ions and write the symbol. So this is more practice. I'm trying to look at the clock. I want to make sure we have time to do some review, and this kind of is some review of what we've gone over. So let me see what we have left. This is, again, just a lot of practice here. So what I'm going to do, I'm going to make a video and walk through these practice problems and post that to Blackboard later today or tomorrow. But I want you to attempt these things on your first on your own. We're going to hit one more. So I'm going to skip over these practice problems. I'll make a video on how I walk through them. Attempt them on your own since you now have all the skills to do that. We're going to talk about a couple properties of ionic solids, and then we're just going to spend the rest of the time reviewing. I wanted to save like 20 minutes or so for review. Okay, properties of ionic solids. So this whole chapter has been on ionic compounds, ionic solids, which is formed by the trading of electrons and ionic bonds. All right. So we've got some unique properties of scientists who studied ionic compounds that we've noticed. They form what we call crystalline solids. Crystalline solids, okay? We call them crystalline because, like example, a sugar molecule, it looks like a little teeny tiny crystal. Salt molecule, it looks like a teeny tiny crystal, okay? We do not call them molecules. I just used the word molecules, didn't I? We call them crystalline solids. And as you're around chemistry for a long time, sometimes these rules get blurred and blended, but that's the proper name. Is ionic compounds are not called molecules, they're called crystalline solids. Some ionic compounds dissolve in water and they form solutions that are good conductors of electricity. Okay, so you've got sodium and chlorine atoms. Remember, when things become a cation, they are smaller. So the purple sphere is smaller as an ion. And when things become anions, they look a little bigger. So you see that change in size. When we put all these together in a crystalline arrangement, we get this nice ordered arrangement like this. And these sodiums, the positive charges, surround themselves with as many negative charges as possible. And same, the negative charges surround themselves with as many positive charges as possible. And you get this nice ordered arrangement. And that's why you see these little crystals down here. If you zoomed in and you could see the size of the atoms, they would actually be ordered and arranged like this. And because we have ions in solution, those things, they're not great conductors of electricity, but weakly they can conduct electricity. Okay, ionic compounds, do you think they're going to have high or low melting points? What do y'all think? And boiling points. High or low melting or boiling points? Looking in the chat, high. That is correct. They have very high melting and boiling points. Why is that? Ionic bonds are really strong because you have a full positive charge and a full negative charge. And remember, opposites attract. So there's a really strong attraction between the cation and the anion. Other bonds, we're going to see later in chapter 4 after exam 1, we don't have the full positive and negative charge. They're sharing electrons. They're not totally giving an electron away or receiving it. So ionic bonds are really strong. And when you have strong bonds holding molecules and holding compounds together, it takes a lot of energy, takes a lot of heat to break them apart. Okay, so to melt them or to boil them. Okay. So they have high melting points and boiling points, and then ionic solids shatter when forcefully broken. Okay, glass. Glass is an ionic compound. We know glass shatters when it's broken. It's just an example. All right. I don't have polls today because I wanted to focus on review. So keep that in mind. That's a little bit about ionic solids. Any questions on what we talked about today? How to name compounds, how to name right formulas for compounds, and a few properties of ionic solids. All right, well, let's get into some review. I want you to grab a blank sheet. Oh, question?
I'm sorry, yeah. I got a question about the writing, like the last ones we did. I don't know. I thought the last one was like we didn't wait. Can you scroll back?
This one right here, ammonium phosphate?
Yeah. When do we still have like ion in the name and when not?
When you're writing the compound, okay, compounds are the combination of a cation and an anion. So when you write the name of a compound, you do not include the word ion.
Oh, okay.
And when you're just
Okay.
writing, if you're just writing the name of an ion, you do include the word ion. Does that help, Zoe?
Yeah.
Okay.
Yeah.
Good deal. Hey, please remember, I'm asking you guys to all have your video on during lecture. Okay. Thank you. Thank you for joining us. All right. Get some blank paper. We're going to have some review. It's going to be timed. It's going to feel high pressure. We're going to simulate the exam. Okay. Get a blank sheet of paper out and get a calculator. I see some of you just looking at me. I'm for real. We're about to get started. I'm going to time you on these problems. I'm not trying to make your blood pressure go up. I am just trying to help you prepare, okay? I think it's good sometimes to work under a clock because that's how the exam is going to be, right? All right. So the first thing we're going to do, I'm going to give you a few minutes. Here we go. We're going to get started. You have 2 minutes. I want you to predict, I want you to write down 9 topics or concepts from chapters 1 through 3 that you think will be on the exam. They can be as specific or broad as you want them to be. 9 concepts, 9 topics from everything we've talked about. Okay? So I'm going to start the clock. Go. If you can do more than 9, do more. Okay, you're a minute in. Give you one more minute. 9 topics or concepts. What did we talk about in chapter 1? What did we talk about in chapter 2? And then even things from today, from chapter 3. Okay, 20 more seconds. If you can go above 9, do it. Okay, we're about to move on. All right, stop. Let's keep going. Classifying matter. I want to know, write down in simplest but concise but specific words, what is the difference between a heterogeneous mixture and a homogeneous mixture? Give an example of a heterogeneous mixture and a homogeneous. You don't have to write a paragraph here, but do try to be specific. I'll give you less than a minute for this question. Okay, about 15 more seconds. Again, I'm not trying to make your blood pressure go up. It's just good. This is good to rack your brain. All right, let's move on. Classify each of the following as either a chemical or physical change. Freezing a popsicle, roasting a marshmallow, bleaching, or coloring your hair. So literally just go through, boom, boom, boom. You can write 1, 2, 3, physical, chemical, physical. You do not have to write down the words. We'll come back to these. Just write 1, physical or chemical, 2, physical or chemical, 3. Give you about 12 more seconds. I'm seeing some questions in the chat. I will answer those once we get through all this review stuff. All right, you should have that. If you feel like we're moving fast, we are. I want to get through it though. We'll come back to this stuff. We'll answer these questions. All right, next one. Let's get some math. Grab your calculator. How many microliters are in 1.78 kiloliters? So you need a relationship here. Remember, what's the abbreviation for micro? All right, you're about a minute in. I'm going to give you about 30 more seconds. This should be a one or a two-step conversion. Not a lot of steps here, but you got to know your prefixes. If you get done with that one, move on to the next one. All right, I would say you should be wrapping up with that first one or getting close. Go ahead and start the second one. Report the answer to the following problem in scientific notation. 2.03 times 10 to the power of 11 times 7.44 times 10 to the negative 3. So what are the rules for multiplying numbers in scientific notation? You're like, That's a great question, and I don't remember. About 30 more seconds, and then we're going to move on. We're going to work on this till 9:05, get as far as we can, and we're going to spend the last 10 minutes going over this stuff. All right. If you're not done, I know this is in a rush, but I want to get through it. So we're going to come back. I'm going to move on. Little word problem here. Dr. Michael prescribes 300 milligrams a day of medicine to a patient. Let's just say patient. Each pill has 1.5 times 10 to the minus or 10 to the positive 5 micrograms of medicine. How many pills will the patient need for 7 days? I know microgram, I don't think is one I ask you to memorize. So I could have told you this on the problem previous. Maybe some of you looked it up. But there is 10 to the power 6 microgram in 1 gram. You're like, well, now you tell me. I can be nice when I want to be. So how many pills will you need for 7 days? So you want an answer with units of pills. Give you about 40 more seconds. This one's got a few relationships in it. Again, just give it your best shot. We're going to walk through all these. This is probably the last one we have time for. I think I bombed these. All right, we're about to wrap up. I've given you about 2 minutes on this problem. A few more seconds, and then we're going to spend some time on review. It's 9:05, so I really want to go through these and have time to do that. All right, we're going to stop. So I'll tell you, how you feeling? I think I bombed these. Questions from the chat really quick on the exam. Will we have conversion factors? Yes, we will. Rachel, I can't remember the exam mostly multiple choice. It will be a portion multiple choice. You'll probably have anywhere from 10 to 15 multiple choice questions. Each multiple choice will be worth 3 points. So a third to close to a half the exam may be multiple choice. Is the exam open? No. Anybody want to answer that?
Yes.
Yes, it is. You're like, praise God. Okay. Okay. I had more review. We could have kept going, and then time got us. Okay. So I will post all these slides, and you can work on these questions as review as well. I haven't had a challenge problem. This is a huge problem. This is like a 7 or 8 step problem, and this is my real life, by the way. Newborns and formula versus all that. So I'll post this. This can be for practice. If anybody wants to join my office hour today, we can work through some of these. All right, let's go back up. Where did we start? 9 topics. Let's name them. in the chat. Would you say there's going to be a lot of those challenge conversion problems on the exam? A challenge or conversion problem is probably going to be like an 8 to 10 point problem. All right. Now, that's why I'm going to have you take a picture of that one and upload it. So there's probably just going to be one of those that are at least you take a picture and you upload it. So probably a good 10 points. And I give partial credit. So if you got half of it right, you just didn't know how to finish, I'll give you as many points as I can. That's why I need you to show me your units. Okay, if you don't show me units, I can't give you points. So anyways, there will be one, at least one or two of those. Okay, we got to get through this. 9 topics. Anybody want to help me? Bless your soul. Valence electrons. I'm thinking about chapter 1. We had signs of a chemical change. Y'all are blowing up the chat. Polyatomic ions. I can't keep up with all this. Specific heat, okay? Specific heat. We had temperature conversions. We had to classify matter as a element, compound, heterogeneous, homogeneous. Okay, we had signs of this should say chemical change, by the way. I wish I was writing smaller. So that's 1, 2, 3, 4, 5. We looked at, okay, Dalton's atomic theory. That was chapter 2. We look at subatomic structure, subatomic particles. Sub, should be sub. Okay. Protons, electrons, neutrons, how they're arranged in an atom. So yeah, specific heat. Remember you had I see this in the chat, calories and joules, okay? Units of those things. Density, don't forget density. That was one thing we talked about. Oh, what else? Ions and ionic compounds, ionic bonds. We talked about how to name ionic compounds. All right. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. That's at least 9. So we could have kept going. There's even more. But I think this gives you an overall general view. Hopefully the point of today was for you to say, oh gosh, maybe I'm not where I thought I was. Maybe there's some things that I see that I'm weak on. And that's the point. I want you to tonight and tomorrow spend your time focusing on the things you know you weren't good at. Classify matter. What's the difference between heterogeneous and homogeneous mixture? Anybody want to help us? Both have more than one thing in it, okay? But homogeneous is even throughout. Okay, you could say they're mixed evenly. Good example would be vanilla ice cream. All right, every bite's the same. Sweet tea, every drink's the same. Heterogeneous is not evenly mixed. You could say unevenly mixed. My writing is really good when I'm in a hurry. Not evenly mixed. Okay, what's an example of this?
I put black coffee with creamer.
Coffee with creamer. Hopefully when you mix that though, it's mixed evenly.
Cookies
I don't want to
cream.
Cookies and cream ice cream. E-S. Is it E-M-E? Okay, vegetable soup would be one. You got a bunch of different things in vegetable soup. Every bite's different. Sand and water, Ashton, that's a good one, okay? All right, that's that one. We're gonna move on. We got 5 minutes. Okay, freezing a popsicle, physical or chemical?
Physical.
Keyword, yes, so physical. Roasting a marshmallow, keyword, roasting, physical or chemical?
Chemical.
Yes, the appearance of that marshmallow looks different. You have a burnt substance now on the marshmallow. It's a new compound. Bleaching, coloring your hair, keyword bleaching.
Chemical.
Yes. Chemical change. Okay. Questions on that? Okay, how many microliters in 1.78 kiloliters? Well, I know there's 10 to the 6th microliters in 1 liter, and we know that 1 liter, I'm going to write it this way. If you don't like this way, there's different ways you could do it. Actually, I'll write it the other way. The way I taught you guys is that there is 1,000 liters in 1 kiloliter. So now we're going to start with 1.78 kiloliters. We want to cancel kiloliters. So I'm going to use this relationship. Cancel. And now I want to get to microliters. So I want to cancel liters, and there's 1,000,000 microliters there. So liters cancel. What's our answer here? 1.78 times 10 to the 9, essentially. You should get 1.78. You could write it like this, times 10 to the 9. Is that what y'all got? Okay, that's what you should have got. Questions on that? You see how we're just canceling units? You got to have these relationships. These are key. And then you just start with the number given, cancel the units till you get to the one you need. Okay, report the following problem in scientific notation. So when you're multiplying numbers in scientific notation, what's the rule? You multiply the base numbers, okay, your digits, and then you're going to add the exponents. Okay, so we're going to add the exponents. So what is 2.03 times 7.44? What'd y'all get?
15.1032.
2.03 times 7.44. Whoops, 2.03 times 7.44. Yep, 15.10. And then times 10, we're not done. We're going to have to adjust that because this is not a number between 1 and 10. So then we're going to add the exponents. 11 plus -3 is 8. So now we got to make this a number between 1 and 10. We got to move the decimal 1 place to the left. And we get 1.510. So then times 10, we moved it left, so the exponent increases. This becomes 10 to the power of 9. So review the rules. And that's another topic, scientific notation. We talked about that. So make sure you feel comfortable with these kinds of problems. Oh, we got 1 minute. Last problem. Think I can do this in a minute? Dr. Michael prescribes 300 milligrams a day of a medicine to a patient. Each pill has 1.5 times 10 to the power of 5 micrograms of the drug or the medicine. How many pills will the patient need for 7 days? So I'm going to write out some relationships. We got 300 milligrams of the drug. I'm going to do D for drug equals 1 day. I know there's 7 days is a week, so 7 days. I'm just going to write how many per week then. 1 week. You didn't have to do this. If you didn't do that step, that's probably okay. And then we've got 1 pill equals 1.5 times 10 to the 5th micrograms. But I have milligrams and micrograms here. So I need a relationship between milligrams and micrograms. Okay, so I know there's 1,000 milligrams in 1 gram, and there's 10 to the 6th micrograms in 1 gram. So I'm going to combine those and say there's 1,000 milligrams equals 10 to the 6 micrograms. And I'm going to use this relationship. All right, so I want to know how many pills. I'm going to start with this relationship because that's got pills in it. Start there. So for every 1 pill, it's 1.5 times 10 to the 5 micrograms. I know we're at 9:15. Give me till 9:16, okay? We're almost done. And then I want to cancel micrograms. So now I'm going to use this second relationship down here and plug that in. I'm going to put micrograms on top and 1,000 milligrams on bottom so that micrograms cancel. I know that I need to cancel milligrams now. We got 300 milligrams a day, so I'm going to pick this relationship next. 300 milligrams on top for 1 day on bottom. And then we got to go for 7 days. So we're going to do times 7 days for every 1 week. And milligrams cancel and days cancel as well. Again, if you just multiplied by the 7, you didn't write the per week part, that's okay. Now, when you start this problem, you cannot ignore this 1. It's 1 over 1.5 times 10 to the 5. All right. Did anybody get an answer here? How many pills? Let's calculate it real quick because I got to let you guys go. If you got to go, I know we're past time. Thank you for joining us. I'm going to calculate this answer, and then if anybody has questions, Bradley said he got 14. Can anybody confirm or deny? You got to go. Thanks for joining us. I got an office hour at 9:30. Bailey said that's what I got. Jacob said that's what I agree. Okay, I'm going to say 14 pills.